So similar to what we did in the last two problems of this last section. So again, for exponential growth, I have a is equal to a sub 0 e to the kt, where k is greater than 0. Let me define something called doubling time. Right? Is the amount of time it takes for the initial amount to double in size. And so suppose we start out with a sub 0 objects. Then t sub 2 is the amount of time it takes for a to increase to 2a sub 0. In general, the doubling time is denoted by t sub 2, and it is equal to ln2 over k, the growth constant. Suppose instead we have exponential decay. A is equal to a sub 0 e to the minus lambda t, where lambda here is greater than 0. Then I define the half-life follows. It is the amount of time it takes for half of your substance to decay to, for half of your substance to decay to a size of 1/2 the original amount. So let's suppose that you start out with A0, then T sub 1/2 is the amount of time it takes for the amount to decay to 1/2 A sub 0. In general, the half-life is just equal to ln2 over lambda. And most people have heard of half-life, especially when related to radioactive decay. Intensity of light, I, is just I sub 0 times k to the x, where x is the distance under water that the light is traveling. The Malthusian population growth, well, we've seen this. P is equal to P sub 0 e to the kt. Logistic epidemiological model. So this is a model where you start out with some amount of infectives, and then everyone gets sort of slowly infective, and up until there is some sort of equilibrium that's sustained. So in this model, this is for a for disease that becomes well, endemic in your society. So P is equal to M divided by 1 plus M over P0 minus 1 times the quantity e to the minus kt. So P0 is the initial number that are infected. M is the maximum population size. K is some infectious constant. And so let's do on page 435, problem number 4. Use a calculator to help solve each problem. Okay, so Chernobyl. In April 1986, the world's worst nuclear power disaster occurred at Chernobyl in the former USSR. An explosion released about 1,000 kilograms of radioactive cesium-137 into the atmosphere. If the half-life of cesium-137 is 30.17 years. How much will remain in the atmosphere in 100 years? Okay, so the half-life of cesium-137 is approximately 30.17 years. The initial amount released is 1,000 kilograms. We want to know what happens after 100 years. So we want to figure out the amount that remains after 100 years. Well, I have that A is equal to A sub 0 e to the minus lambda t. So either I can use the fact that we know a relationship between the growth, the decay constant, and half-life, or maybe I can just derive that formula. Maybe I'll derive the formula. Okay, so let me try to use the decay constant. So you could just determine the decay constant using the above formula for half-life, but I think I'll just try to figure it out on my own. So suppose you start out with 1,000 kilograms, and it takes 30.7 years, 30.17 years for you to decay to 1/2 of that, to 500 kilograms. Let's determine lambda. Okay, so divide both sides of your equation by so oh boy, lambda. Okay, so I just divided both sides of my equation by 1,000. Let's take ln of both sides of my equation. Ln of 1/2 is the same as minus ln of 2. Ln e to any exponent is the exponent. Let's divide both sides of my equation by negative 30.1. So negatives cancel, so you get ln 2 over I'm sorry, 30 ln 2 over 30.17. Notice I could have gotten that originally because I know that the half-life is ln 2 over lambda. So lambda is ln 2 over the half-life. And so we derived that, but we also had that formula from above. I have that A is equal to A sub 0 e to the minus lambda t. Okay. So the amount A is equal to the original amount, 1,000 kilograms, times e to the minus lambda. Well, we figured out lambda. Lambda is ln 2, 7. And t was, well, 100 years. And so that's your answer. but you'll probably want to plug that into your calculator. So let's plug this into our calculator. So the amount that you have after 100 years is about 100 kilograms. 100.5126593 kilograms. So that's the approximate amount of cesium 137 that you have. Okay. Let's do problem number 17. Newton's law of cooling. Some hot water, initially at 100 degrees Celsius, is placed in a room with a temperature of 40 degrees. After T hours is given by T equaling 40 plus 60, 0.75 T. Find the temperature in 3.5 hours. And so I want to figure out the temperature in 3.5 hours. I'm given that T is equal to 40 plus 60, 0.75 T. So let's plug in for T, 3.5. And, well, actually, that'll be your answer, but let's plug it in. Okay, I just wanted to check something. Yes, I did actually. Okay. For some reason, I was thinking that I left a gap. Okay, so let's insert a new page here. Okay, so let's plug in to our calculator and see approximately what the temperature is. About, and this is given in Celsius. So you start out with boiling water, and after 3.5 hours, it is still warm, 62 degrees. So 61.9212903 degrees Celsius. Okay. So that's how approximately how warm it is after 3.5 hours. Okay, so let me move this. Probably need to move all this up here. Oh, I don't have enough room for that, I don't think. Let's see. Oh, maybe I do. Yeah, I can do it. Okay. So let's do problem 34, epidemics. In a city with a population of 450,000, there are currently 1,000 cases of hepatitis. If the spread of the disease is projected to follow a logistic function, how many people will contract hepatitis, the hepatitis virus, after 6 years? Okay, so let's do this. So I want to figure out what P is at 6. So I just plug in. So P is equal to 450,000 over 1 plus 450 minus 1 e to the negative 0.2 times 6. Actually, I should say p at 6. Okay, so this is equal to 450,000 over 1 plus 449 e to the negative 1.2. And let's plug that into our calculator. So I get that P is approximately 3,303.086,817. And so the number of infected is approximately 3,304. If you are slightly infected, you're still infected. So we have to round up. We round up to the next person. Okay, so that finishes off section 4.2.